This is a step 3 question from 1997, and I'm just going to go through it and kind of see how it goes. I haven't tried it before, so hopefully I can do it. Okay. So, first part is asking us about I of 0, so that's just when n is 0, so let's do that. So that'll be between root x times root a minus x dx, because the n is just 0. And I guess I'm thinking trig sub here, because I want this root to become like a cos, I think. So I'm going to do x is a sine squared theta. That should work. I told you. So then dx is 2a sine u cos u. Cool. The bounds, so the upper bound when x is a, we have sine squared u is 1. So sine u is 1. So u is just pi over 2. So the upper bound is pi over 2. And the lower bound is, of course, just 0. Okay. Here we have, so we have root a sine u times, well, if we put that in there and then we root, we're going to have root a cos u, and then times the du bit. Should have put a du there. We're going to have times 2a sine u cos u du. Cool. And now I guess that's going to be pi over 2, 0. We can take the a's out, and that's 2a squared. Sine squared u cos squared u du. And then I can factor out a quarter, because I can just make this sine 2u. So that would be, go away. Okay, there we go. A squared over 2 sine squared 2u du between pi over 2 and 0. And then that's just going to be a squared over 2 pi over 2, 0, 1. I guess I can change that to a 4. And then 1 minus cos 4u du, which is just a squared over 4 u minus sine 4u over 4, and then that's between pi over 2 and 0. And then, of course, this, the sine part evaluated at pi over 2 and 0 is just going to be 0. So I guess this is just going to be a squared pi over 8, because it's just 4 times 2 on the bottom. So cool, we've shown that. Cool, the next part, okay, so we kind of just want to do some by parts on in, I guess, because we want this n to be n minus 1. So we're going to be differentiating the left term. So I'm just going to think about integrating this. So if I increase the power to 3 over 2, then I'll get minus, so it's going to be minus 2/3 a minus x to the power of 3 over 2, I think. Yeah, that's right. So, okay. So leaving the first term, so we have x, so I'll just write I of n equals x n plus a half times minus 2/3 a minus x to the 3 over 2 minus the integral of x times n minus 1 plus a half times n plus a half times minus 2/3. Wait, is this right? Minus 2/3 a no, it needs to go there, right? Yeah, and that's a product, so just write that there. A minus x to the power of 3 over 2. Cool. And then that's between, of course, our bounds, a and 0. So if we evaluate this between a and 0, then we just get 0, because this term is 0 for the upper bound, and then for the lower bound, this first term is 0. So I guess in is just, I need to change this as well, don't I? So minus 2/3 times that. So okay, I can take I can take out minus 2/3, so 2/3 n plus a half, and then I'm left over with this a0 x n minus 1 to the half, and then times this a minus x to the 3/2. Wait, where's that come from? Okay, that's fine. Cool. So I think I'm gonna split this up into the root part and like the whole part. So I'm just gonna ignore this bit at the front for now. So I'll have a0 x n minus 1 to the half, or plus a half, and then a minus x and a minus x to the half. I'm hoping I can raise the power here with the x. That was kind of why I'm thinking this. Okay, ax n minus 1 plus a half times root a minus x. Oh yeah, this is looking good. And then dx plus or minus x to the n plus a half root a minus x. And of course this I can just bring to the front, and that is I of n minus 1. So, okay, let's think about this. So we have, I guess if I multiply this 3 up, we have 3in equals 2n plus 1 times a I n minus 1 minus I n. Right? Yeah, seems fine. Is that? Yeah, I mean, the 2n plus 1 looks good. So then we have 3in plus 2n I n plus in equals 2n plus 1 a I n minus 1. Is that what it wanted? Yeah. And is that 2n plus 4? Yeah, 2n plus 4 in equals 2n plus 1 a I n minus 1. Cool. So we have this relation now. And I guess if we have this, and we also have I0, we can work out I1, and hopefully just like keep generalizing. So in equals 2n plus 1 a I n minus 1 over 2n plus 4, and then I of 0 equals that was it pi squared, pi a squared over 8. Yeah, perfect. Wait, not perfect. Cool. So then I1 would be when n is 1, so we'd have 3 pi, wait, I'm going to write it as like two separate things. So 3 over 6 times pi a cubed over 8. I2 would be this part, times by, 5 over 8. So I guess if we generalize this for in, then in would just be, 3 times 5 times blah 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 up to 2n plus 1 over 6 times 8 times blah 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 up to 2n plus 4, and then we're multiplying that by pi a, that should be to the power of 4, because we're adding on an a each time, so it's going to be n plus 2 over 8. I think that's okay. I mean, a definitely increases by 2 each time. We're definitely adding 2 to the thing each time. Yeah, hopefully that is good. Yeah, should be fine. Anyway, thank you for watching. I hope anyone found that useful.